Yeah. Hello everyone. So this is going to be a quick talk. So I have a lot of slides. I'm going to go quickly, but if you have questions, you're welcome to talk to me later. So today we're going to talk about password keepers. In this case, we're going to talk about a small device. Does that work? Yes. Okay, so first let me introduce myself. My name is Mathieu Stéphan. I'm an embedded systems engineer, a former writer for hackaday.com, and I also have a website, and I'm the project founder of the Multipass Password Keeper. So what is the Multipass? The Multipass basically is a small device that is going to store for you your logins and passwords. So why we made it is because we don't trust our computers. So we wanted to have a dedicated device for storing credentials, but also small files. We have a native browser integration with Firefox, Safari, and Chrome. It is recognized as a keyboard, so it will work on any device. It can allow multiple users, cross-platform, and of course open software and open hardware. So exactly what is inside the device? Basically it's a small box which contains a small microcontroller, some screen which allows you to see which website you're approving the credential sending, flash memory for storing the credentials, and a small wheel that you can click in order to navigate through the user interface. The encryption key is stored on a dedicated smart card. So that's great. So what does it look like concretely? You go on the website, the Multipass lights up, and you can knock to approve the credential sending. And you can also use it as a standalone device, so without native browser integration. You use the device, you use the wheel, you go, okay, I want to log in on Skype. So this, for example, is my phone. The Multipass is basically emulating key presses in order to enter your login and password. So today we're going to talk about how this adventure started. So really the goal here is if you have some project in the back of your head, you want to make a device. So this is a few advices. So this will be of course applied to the Multipass Password Keeper. But I hope that when looking at the slides, maybe this can apply to what you want to do during your spare time. So we're going to talk about how this started, how we produced the device, how we created the security model, and how we created the firmware, the hardware, and even the software. Okay, the project. I'm going to go quickly on these slides. It's not the most technical ones, but it's still worth being mentioned. So as I mentioned, at the time I was a writer for hackaday.com, and I figured, hey, why not create a device that everyone can work on? Let's make something open source, open hardware, for the good of the community and to have our passwords stored on a dedicated device. So basically in 2013, I created a small article, basically stating my idea, hey, I would like to create this kind of device. Would you be interested in contributing on it? We got 30 different applications, and from there on, we gave the work based on what people were doing in the first place. Right? So this is the contributors map. So as you can imagine, me personally, I'm located in Switzerland. So when you're trying to work with the guy located in New Zealand, which is 12 hours away as a time zone, this is not the best scenario. So how do you try to work with a team which is located all over the globe? Basically, you establish ground rules. Ground rules, I'm going to go quickly on them. Of course, document the code. I know most of us, we don't like documented code. You know, the code is self-explanatory, right? You don't need to comment it. Actually, we still forced the contributors to document the code. The main reason is why if someone is leaving because he has a job or he has some family reasons, we want the next guy to be able to understand the code, work in dedicated files folders to avoid merge conflicts, and choose coding conventions. I know most of you, some guys like tabs, most like spaces, but believe it or not, we need to agree on that before you start coding. So imagine 30 developers discussing on the mailing list about tabs versus spaces. It was a long night. Group communication. So I mentioned the mailing list. When everyone is in a different time zone, how do you communicate? You want people to feel involved in the project. Of course, you're not going to use one-on-one conversation means. So we used basically discussion groups, Google groups in our case. IRC, it still exists, it's still there, so we use this sometime. And of course, the main goal here was like to keep everyone involved and keep everyone motivated to code. So you have people all over the globe working on a project. How do you see where the project is at? We used Trello. Basically, everyone has a small task. Everyone has a small dedicated card describing what he can do. So of course, you can choose to work on something else, but the goal is at a given moment, if you want to work on something else, you can see what is available. And of course, if something is missing or if something is behind, then at least we'll have a good overview. Yeah, so this is how do you, some management techniques, how do you manage everyone. It's open source. We all have our availability, but you're trying to create a device, whether you want it or not, you still have deadlines. Yeah, so this is a few techniques if you're interested. Anyway, I'll skip over. So now the boring stuff is over. We're going to talk about the hardware, what it looks like inside. So as I said, the goal of this talk is to motivate you to create something, right? So first thing first, you need hardware. In the case of the multipass, I'm an embedded systems engineer by trade, so I like to solder. So the first prototypes, basically you create them, we use KiCad in our case. You create the schematics, you create the layout, and then you spend a couple of days soldering and send the device to the developers. The goal, of course, is to have everyone working as fast as possible. Case choice, we are geeks, we are not good at aesthetics. So luckily on a Hackaday, the readership comes from everywhere, and we basically made a call for case designs. So we had a lot of different artists that contacted us to suggest the different ideas, and we let the Hackaday readership decide. So we basically organized some votes where we want to vote on their favorite design. The first device looked like that, and the second it was funded in 2014 through Indiegogo at the time. And 2 years later, we created a smaller version of the original multipass using still the same methodology. You soldered the first prototype, ship them the contributors, and ask everyone if they have an idea for the case. And we got funded exactly a year ago on Kickstarter. So, concretely, so you've seen before the device is made of aluminum, we are creating a security device. So we wanted something robust, something which was stiff, tough, and just to make sure that actually the aluminum, this is a small anecdote, to make sure that the adhesive keeping the case together was all right. You also have some security guys that contact you, yeah, you're using some aluminum case, so you make sure that it doesn't open easily. So this is basically me standing on the multipass case trying to pry open. But we also have some other guys that wanted to make sure for themselves. So this is one failed attempt of trying to open the device because our complete, the background here is that our complete security model relies on the fact that the device can't be opened physically without leaving traces. There are some traces. So of course, so you have, I mentioned before, you have a few prototypes that you solder yourself. It's not that hard to solder. There are a few workshops this afternoon about that. You have a few prototypes, then you want to go into production. How do you find people? How do you find assemblers in China? Because it's going to be cheaper than if you try to see in Europe. So in our case, basically, this is a small anecdote. I bought a power supply in China, connected to my home, then the complete fuses blew. And I contacted the guy, and basically I discovered that they were able to do device assembly. So we went to I went to China to teach them how can you set up a mass production chain. For the multipass mass production run, we usually produce between 4,000 or 5,000 units because this is the minimal amount for which you will get a good price. You also visit CNC shops in order to see how they can, what are the different mechanical constraints when you want to manufacture something. As you can imagine, if you have an idea of a metallic case, it may not be easy to produce. There will be some constraints. So this is something I didn't mention, but of course you go to China, they don't speak perfect English there. So if you were to do that, one advice that I recommend that I did is to find a Chinese wife. She does the translation. I cheated, I know. So I mentioned communication problems. This is, if you want to manufacture something, the usual way of doing things is that you make a small document explaining how do you assemble the device, how do you make the functional testing and everything. But this is a document, this is written in English. It's not the best way of doing stuff. So in our case, if you want to teach some Chinese assembler to do something, one way we found very effective was basically to make a video. So basically you make a small, you put a small camera on top of you and you explain the different functional testing, what you need to do. So this is me basically connecting the device, explaining the functional test, and on the bottom right you see what the assembler would see on his screen. So this is the functional test running through. You can't think of everything. So of course there are going to be some hiccups. My advice to you if you were to create some device is that prototype. Before we went through the mass production, we actually hired the assembler to make small batches of 50 units. When you assemble the device on your own bench, of course, it's your device, you're going to take care of it. But when someone else is going to assemble the device, he's going to take a lot of shortcuts. So this is one result of the first 50 units batch. Basically, when you assemble the case, you put some adhesive, some glue. So the assembler figured, hey, there is glue, I just put it somewhere and it will dry off, right? But yes, he put too much glue, didn't let it dry, and this is like glue traces all over the place. So there are, as with any mass production, there will be some unknowns. So produce small batches of 50 or 100 units to discover what could go wrong. Firmware, already at 15 minutes. Firmware, so we are creating a security device. So we don't want to use any libraries, we don't want to use anything that we don't know what it is doing. And the only exception to that rule is crypto libraries. We don't want to reinvent the wheel. We are not cryptographers, so what we can actually do is use a library and implement the different functional testing in order to make sure that the library correctly behaves. So for this small device, we are using AVR Cryptolib. It's to do the small encryption functions. It takes a little while, but that's perfectly fine. We don't have heavy performance constraints. Encrypted storage. So we have sorted link data structures to store your credentials and files. So what it looks like is something like that. So this is our own database implementation. We made it this way in order to be quick when the user is browsing through the credentials, and all the different credentials and data are encrypted using a smart card that contains the encryption key. Finding a smart card that can store an encryption key is surprisingly difficult. It took us, I think, 2 or 3 months contacting NXP, basically all the big players out there. And when you're a small company, and not even a company, and you don't want to order more than 10 million smart cards, they are not going to want to sell you the smart cards. And when they hear that you like open source, forget about it. They don't want to, it's not possible. The data sheets, I know, for example, the guys at ANSI or whatever that have access to the smart cards, they are required to sign NDAs to not divulge the different intricacies of the smart cards. So in our case, we found basically it's a read protected memory. You enter a PIN code to unlock the contents. The contents are the encryption key, and it is quite cheap. It's something simple, but it does the job. Random number generation. How do you generate that encryption key? In our case, we use a small algorithm that uses the jitter between the watchdog timer, so basically it's a small oscillator, and the external crystal oscillator of the microcontroller. So apparently this is a very reliable way of getting random numbers, but you only get 8 bytes per second. Doesn't look much, but it's actually perfect for what we want to do, to generate an encryption key and to generate some padding. USB. So you've seen in the first animations that we have native browser integration. So basically for that particular feature, on the USB layer, we have two communication links. We have one communication channel that basically implements HID proprietary, which is just a fancy way of saying that you're sending 64 bytes every millisecond. And in the other animation, you've seen that actually you use the multipass to specify which login and password you want entered on your device. So for that particular feature, you're using HID keyboard. So we are basically, the multipass is basically a smart keyboard. It is going to tell the operating system, hey, the user has pressed that key. But unfortunately, for the HID keyboard protocol, the keyboard is not telling your computer, hey, the user has pressed, hey, A or B or C. The multipass is telling the computer that the user has pressed the key which unique identifier is, for example, 52. And then it is up to the computer to do the translation between this unique key code to the ASCII character. So this is based on your locale. So on your computer, you choose, for example, French layout or English layout. So this is quite a constraint for us because we need to know which kind of unique identifier we need to send to the computer in order to get an A pressed on the computer. So how do you generate these lookup tables? So what we have done is actually a small script that basically brute forces all the possible key combinations in order to know which unique key code maps into which character. The small scripts that takes a minute to run, but at least we can generate the lookup tables between key codes and ASCII characters based on the computer locale. Graphics library, also generated from the ground up for speed. We implemented run length encoding to compress all the different bitmaps, fonts, which are stored in the external flash. We have a complete set of Python tools in order to generate this binary data. And the complete graphics bundle can be securely updated. So we already had AES encryption routine on the device. So we figured, okay, how are we going to implement digital signing? So this is in detail how the update protocol is implemented for given. So when basically you update the device of your multipass, it is going to update the graphics, the firmware, and if you want the encryption key stored on the device. So this is what we send. We can update the encryption key of the device because each multipass has an encryption key that allows for the secure updates, and everything is used with CBC Mac. So if you plan to use CBC Mac in the future, don't. It has some security. It's really hard to use CBC Mac in a proper way, so it took us quite a while to implement it this way without falling into the different traps of CBC Mac usage. Bootloader, I said that we have a way of updating our device. We have unique encryption key per device in order to, for example, if someone wants to open a multipass device and hope to find an encryption key that he could use to generate malicious updates on all the other devices, it is not possible. Each device has a unique AES key for that will be used in order to make sure that the update that you send it is the correct one. Security model, I mentioned that we rely on the fact that any attempt on the device case can be seen, and also on the fact that if you try to reprogram a given microcontroller, it will first require a chip erase, so it will erase any encryption key and everything that is stored in it. So I can answer the different mechanism questions later after. So now that you have created a firmware, how do you make sure that it is secure? How do you make sure that it is bug-free, hopefully? We had a lot of different security groups that contacted us in order to make static analyses. So we spent many nights making sure that we didn't have anything wrong, badly implemented. Luckily, we didn't have any bad surprises. It seems that we were okay. Apparently, we did a good job. That's cool. But now we had another constraint, is that once you've created your firmware, how are you going to flash it into your microcontroller? How are you going to make sure that what you compile is the one that is going to be shipped to your customer? So in our case, I decided to do it myself. So I spent 5 days in China, basically taking each microcontroller, putting them in the different slots in this bench, which then would do the programming. So I programmed, I think, 5,000 microcontrollers myself. It was a tedious process, but it was done. So actually, this way we could have the insurance that what was compiled was actually flashed into the microcontroller that would be shipped to the customer. Software, so now we are getting to the very high level. We have different tools to implement native integration into your browser. We have a Python tool created by one contributor on his spare time, completely alone. So it's a Python tool that will allow you to, it can be called from any application that will allow to recall and store credentials and also small files. In the beginning, we had a unique constraint. Basically, you want to create a very nice way of, a convenient way of providing native browser integration. You want, as I showed in the first slides, you want basically to go on a website and then to have your device wake up and ask for your approval. So you need some way to integrate into, for example, Chrome, and a way that will be cross-platform compatible, that will work on Windows, Linux, and Mac, which is why in the beginning we went for Chrome, because they provide APIs that allow you to basically talk USB without caring about all the boilerplate code that is inherent to any operating system, and it is a 2-click installation. So just with JavaScript, I don't like it more than you do, but with JavaScript actually you can have something talking USB and which is cross-platform compatible in no time. So this was the first approach, and later because we wanted to make it a standalone application, we use Electron to make it a standard X file. So Electron is not that pretty. Basically, it's a framework that runs a browser on your computer and that will run your app. So which is why lately we have released a new tool, which is coded from the ground up in C++. It is called Multiqt. It's composed of a daemon that always runs on your computer that takes care of the communication between the different extensions on each browser and your device. It has an SSH agent, so basically you can log into your server using SSH keys that are stored on your device. And it has a very nice user interface that allows you to visualize the different logins and passwords stored on your computer, and also small files. So what's next? Here I'm going to introduce the next multipass we are currently working on. So this is, we are completely changing architectures. We are using 2 microcontrollers. One microcontroller that is considered unsafe, which is in the unsafe domain that talks USB and Bluetooth. I know that Bluetooth is not the most secure protocol, so actually on the device itself, the secure microcontroller would be able to disable the Bluetooth chip. So actually you can still use it as a standard multipass. It can be battery powered, and we are going to implement much needed features such as Unicode support and new bootloaders, second factor authentication. So if you're bored and you don't know what to do, you send me a message. So if you're interested in working on the firmware, on the software side of things, what is great with multipass is that, as you have seen, we have worked on hardware, firmware, software, on design, and now we're going to work also on for example, creating users' profiles on the internet. Thank you for listening, and if you have any questions.
Thank you for the great talk. We have time for a question. Yes, on the left.
First of all, thank you very much for your talk. Do you plan to have your tool certified by something like ANSI or something like that?
So actually, I'm in contact with the ANSI guys. So actually, they have one of the picture of the static analysis you've seen in the slide. It comes from ANSI actually, and yeah, I shouldn't say that, but they are using a couple of them.
They need to test it. Other questions, comments? Yes.
I was just wondering, you said after like 4 incorrect pin attempts, the device is locked. So is there a way to unlock it again, or is like all your passwords are lost at that point?
So we implement the feature of making clones of your smart card. So actually, this is actually the device is shipped with 2 smart cards. You make a new user with 1 card, then you clone that card into another one. Then of course you don't want a way to reset the reset counter, because anyone could just use your smart card and try until it gets the correct pin. So yeah, in practice you have 4 times multiplied by the number of smart card clones you have made.
Other question? Yes? No. For the video, you need to talk on the mic.
Thank you. Is there a way to securely back up the contents of the multipass on some place? Because if it gets stolen, obviously you lose everything. So.
That's the beauty of it, because your database is encrypted on the multipass itself. So basically, you can export it to anything. You don't care; it's encrypted in it.
Other question? So I have one. What is the price of this device?
In the worst case, it's open source and open hardware, so you can make it yourself. We sell it on the internet for $79. So I didn't talk a lot about how you price a device. So in theory, the rule of thumb is that you have your costs, you multiply by 2.5, and then this is your resale price. But actually, we do less than that. I think the cost is between $55 and $50. The goal here is not to make money. I'm not paid by that project, but is to make money in order to hire people that we couldn't find contributors on. For example, C++, we don't have a lot of C++ contributors, so for the last 3 months, I've hired someone in order to implement features that were required.
Okay, thank you again.